In this lesson, we're going to take a closer look at how frontier molecular orbital theory can help us explain the experimental observations we observed in the last lesson, as well as observations about other cycloaddition reactions. So we're going to begin with the Diels-Alder reaction, and first look at the transition state in orbital terms, and see how it explains the origin of stereospecificity in the reaction. So the first thing you should keep in mind is that as the two reacting partners approach one another in the Diels-Alder reaction, they do so in a parallel fashion. So the two planes in which the pi systems reside approach each other in a parallel manner. Because the two bonds that form at the same time, the substituents off of each reacting partner are forced to maintain their positions throughout the reaction. As a result, their stereochemistry is maintained in the product. The relative stereochemistry of substituents is determined by their relative positions in the transition state. So notice that substituent B in the dienophile and substituent E on the diene are on opposite sides of the newly forming bond. As a result, we see that substituents E and B end up trans in the product. Similarly, substituent C is on the same side as substituent E in the diene, and so we see that those two substituents end up cis in the product. This doesn't explain why the dienophile orients itself the way it does. In fact, we'll get to that in a second. But it does show how we can go from the position of the atoms in the transition state to the position of atoms in the stereochemistry in the product. You'll want to have the ability to draw the stereochemistry of any Diels-Alder product quickly and easily. The easiest way to do this is to pick a transition state and draw it from a top-side view, placing the substituents on the same side of the newly forming bonds with the same stereochemistry in the resulting product. The schematic at the bottom of this slide shows you how to do this. In the reaction of this diene with this alpha-beta unsaturated aldehyde, we can see that the transition state will likely involve the diene and the dienophile approaching each other in parallel planes, one on top of the other, and that's drawn for you here. Notice that we've placed the aldehyde group on the left-hand side because the dienophile is likely to approach in an endo fashion, and this represents the endo approach of the dienophile. Placing the reacting partners one on top of the other, we see that the newly forming bonds are here and here. And what you should notice is that the substituents that are on the same side of these bonds will end up cis in the product. So in other words, these two hydrogens will end up cis in the product, and sure enough, we've drawn them both with wedges, and the aldehyde and the methyl group will end up cis in the product, and sure enough, we've drawn both of these with dashes in the final product. We can look at the other end of the diene and draw the same conclusion. So this H is on the same side as these two other hydrogens, and so we would expect it to have the same stereochemistry as those hydrogens in the product, and sure enough, it too is drawn on a wedge in our predicted Diels-Alder product. For an example to work on your own, see if you can draw the endo transition state and the endo product for the dimerization of cyclopentadiene through the Diels-Alder reaction. Now let's discuss why the dienophile orients itself the way it does in typical Diels-Alder reactions. So there are two ways the dienophile could theoretically orient itself, either exo or endo. If the substituents on the dienophile are far away from the double bonds of the diene, then we call that the exo transition state, whereas if the substituents are near the double bonds of the diene, then we call that the endo transition state. And a number of observations have supported the idea that the endo transition state is lower in energy than the exo transition state, because the endo product is often observed to be formed faster than the exo product. And you might think about how the transition state energy relates to the rate of reaction for the endo and exo products. The explanation that's typically offered for this is that secondary FMO interactions stabilize the endo transition state, but not the exo transition state. Notice that when the dienophile approaches with its substituents endo, any p orbitals on the substituents can interact with the back p orbitals of the diene. So for instance, the p orbitals in the carbonyl groups of this anhydride here can interact with the p orbitals on the diene that are not participating in the bond-forming event of the Diels-Alder reaction. This secondary interaction, while it doesn't form any chemical bonds necessarily, does delocalize electrons and as a result it stabilizes the endo-transition state over the exo. Of course, in the exo-transition state, those same p orbitals of the carbonyls are much too far away to interact with the orbitals on the diene. Here you can see sort of a head-on view where the orbitals participating in the bond-forming events are here in front, and the secondary orbital interactions are labeled in the back with these red arrows.